calculating the pH of a buffer solution. So if you find these questions a little bit confusing, just start with writing out the dissociation of your weak acid and the complete dissolution of your salt. So it doesn't matter what the acid is, chloroacetic acid, what on earth is that? Right, we can tell that it is going to donate a proton, which is going to be accepted by the water. So the water is going to be acting as a base in this situation. So what's left over if we donated a proton, CH2ClCO2 minus, will be the conjugate base and will be generating hydronium. And of course, because that is a weak acid, it's not one of the strong ones, so it must be a weak one. That is going to be an equilibrium situation. So we can draw our backwards and forwards equilibrium arrows. So our salt, we're going to assume, is going to be completely soluble, will totally dissociate in aqueous solution. So this writing it in a molecular kind of style is not really accurate for soluble ionic salts. It's going to break apart into its cation component and the anion. And remember, anions can either be basic or neutral. So sodium would be a neutral cation. Cations are either neutral or basic, neutral or acidic, and sodium is the conjugate counterion of a strong base, sodium hydroxide, so that's going to be neutral. But this ion right here, the chloroacetate ion, is going to be basic because it is the conjugate base of a weak acid. Look, we have a match here and here, okay? So this is going to be a basic salt. So the base component is going to be the concentration of this chloroacetate ion, and that is coming from the complete dissociation of the sodium chloroacetate. So if we have our concentration of sodium chloroacetate, 1.3 molarity, look at the stoichiometry. For every 1.3 molarity solution of sodium chloroacetate, we have a 1.3 molar solution of sodium ions and a 1.3 molar solution of the chloroacetate ion. So if you need to write out your mole ratio as a conversion factor, if that helps you, just to make sure you know where that is coming from. A lot of the time we're going to see this is going to be like a one-to-one stoichiometry, but you may need to do a conversion if it yields more than one anion, right? So look at the formula of the salt and that will guide you. Like if it was strontium was the cation, then for every 1 mole of salt we'd be yielding 2 moles of conjugate base, right? So just watch for that. Okay, so this is the basic component, and the acidic component is, of course, going to be our weak acid, which is the 0.77 molar solution. Okay, so you take those initial concentrations and stick them into your Henderson-Hasselbalch equation, which is pH equals pKa plus log of the concentration of base over the concentration of acid. And this works because of the X's small approximation. This is essentially what you would end up with if you used an ice table, but this is just going to be a lot quicker as long as the X's small approximation is valid, which usually it will be with buffer solutions because the presence of that common ion from the basic salt is going to suppress the ionization of the acid. So one problem is we don't have pKa, we only have Ka, but remember P equals minus log, okay? So pKa, if I can write it, is minus log of Ka. So that's going to be minus log of whatever Ka is, 1.3 times 10 to the power of minus 3. And that's going to give me Ka for the chloroacetic acid, which is going to be 2.88, leave a few sig figs, 6.1. So now we can calculate our pH. And of course, you can do the same thing if you have a buffer that is of the form of a weak base with its conjugate acid dissolved in it, but you will need to work out Ka for the conjugate acid of the weak base. So if you've only been given Kb for the base, you're going to have to convert that into Ka for its conjugate acid and then Ka to pKa. Okay, so just watch out for that. So log the concentration of the base is 1.3. And the concentration of our acid is the 0.77. So do make sure you get those the right way round, otherwise you're going to end up with calculating the wrong thing. I didn't write in what the pKa is, silly me. So pKa, which I now have calculated, that's talking for you, is 2.88. 0.61. That's probably plenty. Sorry, I didn't put that in there. So if I stuff that in my calculator, I'm going to get pH equals 3.11 to 2 decimal places. Okay. Now, you were done with the question, it is good. But to be absolutely thorough, I'm going to check the X is small as approximation, which means that you have less than 5% ionization of your acid. So what I have to do actually is from the pH calculate my hydronium concentration. Like I say, this is just me being extra super duper pedantic, which is 10 to the power of minus pH. If you remember rightly. So 10 to the power of minus 3.11 gives me 7.8, let's call it, times 10 to the power of minus 4. So I can just tell from looking at the relative order of magnitude, 10 to the minus 4 versus 0.77, that we're going to be less than 5%, but we'll do the math anyway. So 7.8 times 10 to the power of minus 4. So that's how much hydronium's actually ionized out of the concentration of my weak acid times 100 to convert to a percent, and that comes out as 0.1% ionization. So way less than 5%, very small amount of ionization. So the Henderson-Hasselbalch equation is perfectly appropriate to use.